Hi everyone, and welcome back to Philosophy of Cognitive Science with me, Dr. Josh Redstone. Today we're going to start the first of our lectures on robotics and artificial life. Before we do that, just a quick sort of recap and plan for today. Of course, it's been a little while since I delivered my last lecture. Apologies, I'm still in the midst of catching up. Luckily, next week is reading week. My hope is that after reading week, I will be caught up to the point where the lectures will be back to going live on Tuesdays and Thursdays. But in any case, you can still treat this as a sort of asynchronous class. And if you, like me, are having a little bit of difficulty negotiating your workload, do get in touch with me. We can make some arrangements. All right? So of course, last time, we covered the points of discussion in the 5th chapter of Clarke's book, Mindware. And today we're going to begin the 6th chapter, which, as I mentioned, is all about robots and artificial life. I'm not going to go into too much of the recap on the points of discussion. Just remember that the last chapter drew attention to questions about mental causation in neural networks, the importance of paying attention to body morphology, temporal dynamics, environmental structure. We're going to touch upon a lot of those same ideas that we covered in Chapter 5 in Chapter 6. So keep your eyes peeled for those themes. Now, so far throughout this class, we've had the opportunity to look at a little bit of robotics research. A little bit of robotics under the classical symbolic framework, like briefly I mentioned Shaky and directed you to a video of the robot Shaky. And of course we saw examples from the new robotics. These would be behavior-based robots created by Rodney Brooks. These robots, of course, don't work with central planning over complex representations. Rather, they're like a collection of reflex agents that respond directly to the environment and kind of work in concert thanks to something called the subsumption architecture. When one behavior is achieved, another behavior takes over. Thus, when Herbert the can-collecting robot finds a table, it can stop and center itself and scan for a can, which initiates a can-collecting behavior, and so on and so forth. Now, all of those examples from robotics, the new robotics primarily, fall under the umbrella of artificial life. And research in the field of artificial life is characterized by 3 themes, which Clarke outlines at the beginning of Chapter 6. And the themes are, number 1, interest in complete but low-level systems. So here we're talking whole, relatively autonomous systems that sense and act in real environments, just like behavior-based robots like Herbert, or a Roomba vacuum cleaner, if you like. The second theme that characterizes research in artificial life is recognition of the complex contributions of body, action, and environmental context to adaptive behavior. And again, we've seen this with, for example, Herbert the can-collecting robot again. And the third theme is that research in artificial life pays special attention to issues concerning emergence and collective effects. Emergence is a really sexy idea that you hear tossed around a lot. But as we'll see in the second part of this lecture, we are still not exactly sure what we mean by emergence. But basically, emergence has to do with complexity arising out of simplicity. Beyond that, there is some disagreement as to the best way to explain what exactly emergence is and how it comes about from collective effects. But in any case, these are the 3 themes which Clarke says characterize research in artificial life and within the new robotics, which is like a subfield of artificial life. So you can find those 3 themes listed on slide 3, and when you move on to slide 4, we can see an outline of the examples that Clarke uses in this chapter to try and make these themes a little bit more concrete. So for theme number 1, which is interest in complete but low-level systems, these are, again, whole autonomous systems that sense and act in real environments. We're going to take a look at cricket phonotaxis. I'll explain what that means in a moment. But basically, we're going to see how research in artificial life is interested in this first theme by looking at Barbara Webb's research on implementing cricket phonotaxis in a robotic cricket. For the second concrete example, we're going to look at walking robots. We'll look at walking robots to illustrate the second theme, which is, of course, recognition of the complex contributions of body, action, and environmental context to adaptive behavior. Walking robots, we'll start by talking a little bit about a robot you'll probably all be familiar with, Honda's Asimo, but then we're going to move on to something really interesting, dynamic passive walkers. So that'll be really cool. Finally, to illustrate the third theme, which again is the special attention that is paid in this research to issues concerning emergence and collective effects, we will look briefly at modeling bird flocking and fish schooling behavior, and then move on to termite nest building and a discussion of something called stigmergy. So those are the three concrete examples: cricket phonotaxis in a robot, walking robots, and termite nest building, to illustrate these three themes. Let us get started by talking about cricket phonotaxis. Firstly, what is cricket phonotaxis? Well, I'll tell you exactly what cricket phonotaxis is once I've set up our discussion for the examples of theme number one. So let's get started. All right, so cricket phonotaxis in robots as an illustration of artificial life's interest in complete but low-level systems. The kind of complete but low-level systems I'm talking about here are, of course, examples like the behavior-based robots we've already seen. If you recall, the can-collecting robot Herbert from my previous two lectures. Incidentally, a neuroscientist in the 1950s from the United Kingdom named William Gray Walter did something very similar to what Rodney Brooks did with his behavior-based robotics approach in the 80s and 90s. Gray Walter created these cybernetic turtles, or tortoises as he called them, which would navigate around the room by responding to the intensity of a light source, bumping into things to avoid obstacles, in one case, going back home to its charging station, just like a modern-day Roomba vacuum. And these are very interesting examples because they're cybernetic, and basically what this means in the context of the work that was going on in Gray Walter's day was that these were behavior-based robots. Simple, sort of two-neuron brains that directly responded to the world and directly activated the robot's actuators. So it's a direct sense-act cycle, not a sense-think-act cycle. I'll link a video in the description so that you can see Gray Walter's tortoises Elsie and Elmer in action. There's also a link to the video on slide number 5. Now, somebody like Daniel Dennett has argued for the importance of studying whole simple systems like this, rather than just isolated aspects of cognition that were studied by Newell and Simon, for example, under the symbolic paradigm. So rather than studying an isolated aspect of general cognition, like for example, playing chess or problem solving, what Dennett argues for is studying whole simple systems that don't do a whole lot, but still manage to do it autonomously, doing things like sensing and acting in a real environment, right? Rather than just some disembodied AI that does one thing only, like play chess. And there are very good reasons, Clark says, to take an approach like the one that Dennett suggests in his 1978 paper, Why Not the Whole Iguana? One reason has to do with solutions to complex problems. Solutions to complex problems, as I talked about last time, that is, solutions we reach via reasoning and planning, may be shaped by pre-existing solutions to basic problems, like sensing the environment, locomoting around the environment, selecting what actions to perform within that environmental context, and so forth. So, during the last two lectures on perception and action in the brain, we saw that there were really good reasons to question the separation of even just basic functions like sensing and locomotion and action selection, since these are often interrelated. They're interrelated because of the way that life forms on Earth have evolved, and in design cases, they're interrelated in, behavior-based robotics in a way that is a lot like the way perhaps rudimentary natural perceptual and cognitive systems have evolved. So let's call this approach suggested by Dennett the whole systems approach of studying whole simple systems that display action, sensing, planning, and so forth. And we'll illustrate this approach, of course, by examining Barbara Webb's work on cricket phonotaxis. Now, I'm going to finally explain what phonotaxis is. Phonotaxis is the ability to detect a sound and reliably move toward the source of that sound. Why is this important for crickets? Well, crickets sing, as you know. They sing by rubbing their wings together. In fact, male crickets sing to attract a mate, right? They rub their wings together, or they rub their legs on their wings. It's a little different from species to species. But they rub their legs together or their wings together, and they produce this tone. And the tone is like the carrier frequency. But if you've ever sat outside in the evening and listened to the crickets chirping, you know that cricket song also has a kind of rhythm, like a kind of pulsing to it. So the rhythm of a particular cricket song is an indicator of what species of cricket we're hearing. And the loudness of a tone, that can be an indicator of how desirable of a mate that this singing cricket is. If a male cricket is singing the loudest song, that's attractive to female crickets, I suppose. Now, phonotaxis is important for the female crickets because they've got to listen to this song and they've got to find the sexy male cricket who's singing the loudest out there in the grass. Specifically, what the female cricket has to do is be able to hear and identify the song of her species. She has to localize where that sound is coming from, and then she has to navigate toward the source. She has to locomote towards the source of that sound once she's identified it. Now notice that we have right there, the way I just put that, a fairly nice task description. Recall, task analysis from our previous chapter when we talked about Mars levels. When we describe it like, step 1, hear and identify the song of her species. Step 2, localize the source of the song. Step 3, locomote toward the song. That's nice. That's a little neat. But it's a little bit misleading as well. It turns out that although this is a neat task description that sits well within Mars, kind of task analysis project at the computational level of analysis, it doesn't really describe what the cricket is actually doing, what the female cricket is actually doing. If you were to start there with that kind of task analysis of female cricket phonotaxis, you might be tempted to conclude that crickets have evolved some kind of central cognition, which is, basic, but still complicated enough to perhaps operate over complex representations of cricket song, to perform that series of steps in the task in a kind of production rule way. If song equals song of one's own species, then localize the source of the song. If the source of the song is located, locomote towards the source of the song, so on and so forth. It's tempting to think that that's what a female cricket is actually doing, using a sort of central cognition, a sort of cricket CPU to operate over these general representations, to make a plan, and to execute the plan in a series of steps that we could characterize with production rules. But that's actually not what's happening when crickets use phonotaxis. Rather, as Barbara Webb has shown, by using knowledge of cricket anatomy, by the way, that's very important, she has shown that we can implement a much more natural means of cricket phonotaxis in a robot by focusing on not a task description of what female crickets do, but rather by focusing much more closely on the implementational level details of cricket neuroanatomy. So, to understand Webb's project, we need to brush up on our cricket anatomy a little bit. And by the way, I'm going to put a diagram of what I'm talking about. It shows in figure A the ears of a cricket, if you like, and in figure B it shows how the sound behaves relative to the ears and the way that the cricket is positioned and whatnot. But anyways, the physiological details that are important here. Let's go. Okay. Crickets' ears, or their tympanum, are actually located on their forelegs. But they also open at two other points on the cricket's body. These are called spiracles. So if you look at the diagram here, you can see the left and the right tympanum on the forelegs of the cricket, but you can also see the spiracles on the sides of the body. And of course, they are all connected together via this tube called a tracheal tube. Now, this means, because crickets have a kind of main ear on their forelegs and other holes or spiracles elsewhere, it means that sound is going to arrive on all these different ear channels via different routes, right? We're going to have a direct external route. That's the route from the sound coming from the environment to the tympanum on the cricket's forelegs. And we're going to have an indirect internal route, which is the sound traveling through the spiracles and reaching the other ear via the tracheal tube, perhaps. So, sound is going to take more time to travel the inner route than it's going to take to travel the outer route. And moreover, the sound reaching the external ear closer to the source of the sound is going to reach there faster than the sound going to the ear that is distal from the sound. So, as a result of all of this cricket physiology, which again, take a look at here, as a result of the physiology, the sound arriving at the direct channel are slightly out of phase with the sounds that are arriving at the inner channel, okay? And don't worry too much about this if you're not sure about psychoacoustics and all of that stuff. Just know that the sound waves, because one ear is farther away than the other, are going to be kind of slightly shifted away from one another. In other words, if you were to plot the sound waves on an oscilloscope, they wouldn't perfectly overlap like this. They'd be kind of shifted like this. Okay, so the sound arriving via the direct and the indirect channels is out of phase. Okay, what's the big deal? Well, the big deal for a cricket, if you're a female cricket, is that your little cricket brain has neuronal circuitry that will sum the out-of-phase waves, the out-of-phase sound waves, and create, ultimately, a louder perceived sound at the ear nearest to the sound source. It's a bit like if I were to play my guitar here and sit like this, the sound reaching this ear is going to sound louder than the sound reaching this ear, because, of course, my ear is closer to the source of the sound, right? Similar for the cricket, hearing the male cricket song. Now, the cricket perceives the loudest sound at the ear closer to the source, and it's able to do this because of the out-of-phase waves that are arriving via the direct tympanum route and the indirect spherical tracheal tube route. Now, when a critical level is reached, a critical level of volume or loudness, there are the intraneurons, one intraneuron in each of the cricket's ears, will fire. The one nearest to the source of the sound will fire first, if the sound is loud enough. And the cricket's nervous system is actually wired in such a way that the cricket will turn toward the direction of the intraneuron that fired first. So if a cricket is facing the same way I'm facing, and the source of sound is coming from the left-hand side, and it reaches this critical level, the intraneuron in the left ear will fire first, turning the cricket, causing the cricket to orient towards the source of the sound. And it'll kind of continually do this until it's pointed in the right direction. So, with each burst of the male song, the female cricket gets a kind of a clue where she can automatically orient herself to the source of the sound. And again, you can kind of see this in figure B of this diagram that I've put up here. This diagram, by the way, is from a publication by Petru, published in 2012. You can see the diagram on slide number 9 if you want to take a closer look at it. But that is the basic story. We have a direct and an indirect channel. We have sound sources out in the environment. The sound arrives differently via the direct and indirect channels, so the sound waves are out of phase. The cricket's brain is wired in such a way that it uses this out-of-phase information to determine where the sound is loudest, and that's the source of the sound. So it's identified the cricket sound from the right species. And because of the way these intraneurons and the rest of the cricket nervous system is wired up, it just kind of automatically orients itself to the source of the song, because the intraneuron closest to the source of the song will fire first and automatically cause a motor response such that the female cricket turns in the appropriate direction. Now, of course, Webb implemented this in a couple of robots, which you can read about in Clark. And the crickets, whether we're talking about biological crickets or robotic crickets, do not possess any kind of general mechanism for identifying sound direction. They don't possess the ability to actively discriminate between even their own species and other species' songs, or even the sounds that other insects make, like perhaps grasshoppers or cicadas, right? In fact, other sounds from the environment cannot generate this directional response. Crickets have evolved so that only cricket songs from the same species will generate this directional response and cause the intraneurons in their cricket brains to reach that critical threshold that generates the turning response. So the cricket, again, biological or robotic, is not applying some kind of general purpose strategy to a specific domain like mate selection. And it's not creating a detailed representation of the world. Rather, like a behavior-based robot, it is responding directly to the world. It is not a sense-think-act cycle. It is a direct sense-act cycle. So, instead of using a sort of general cognition over rich, complex inner representations, what crickets, biological and robotic, seem to be doing is exploiting an efficient special purpose strategy. The cricket doesn't need anything like what we call representations or inner symbols under the symbolic paradigm to do any of this. Rather, as Webb argues, this is completely unnecessary to explain what crickets are doing when they use phonotaxis. These crickets are much more like Gray Walter's tortoises, or much more like Rodney Brooks's creatures, or a robot like Herbert. Here, our descriptions need to be attuned to implementational details and not to information processing accounts. Because even though there is arguably some information processing going on in these cricket auditory systems and cricket brains, they are not doing things the same way, for example, Shaky the robot is doing. They are, once again, doing things in a much more similar way to a robot like Herbert. Direct sense act cycles that allow the cricket to locate the source of the sound and navigate towards it. And as far as identifying the source of the sound, the cricket's ears respond appropriately to sounds made by members of their own species, but not to other sounds. So they're just kind of hardwired to work this way. And crickets, and indeed insects, I think, are fascinating this way. They are like naturally evolved robots. Very fascinating. Now, this isn't the whole story, and that's because crickets also possess something called the optomotor reflex. What is the optomotor reflex? Well, the optomotor reflex is a reflex that responds to changes in the cricket's visual field by turning the creature in the opposite direction. Again, automatically. And this is to compensate for unintended motions or changes in direction. You know, when you're a cricket, you're hopping around on the grass and doing all your cricket stuff. But, you know, things move, the wind blows plants and branches around, and you can get moved around unintentionally. And this way, you can kind of reorient yourself automatically just because of changes in your visual field. You know, so if I'm supposed to be heading straight that way and some wind blows me to face this way, the optomotor reflex will cause my cricket legs to automatically reorient me back in the direction that I'm supposed to be facing. But this will conflict with the phonotactic strategy that the female cricket needs to find the male cricket who's singing. How do we cope with this? How do we deal with this? How does the cricket deal with this? Well, Webb and her colleagues examined a few different ways that crickets might compensate for the optomotor reflex while engaged in phonotaxis. And the best solution they identified when they implemented in a robot cricket turned it out to be what's called an efference copy. An efference copy is a copy of a motor command that's fed forward into a kind of a simple model that predicts what the altered visual inputs should look like. So basically, this efference copy is used as a kind of prediction that inhibits the optomotor reflex with respect to only the relevant motor behavior, the relevant motor responses that are involved in phonotaxis. So in other words, our female cricket is engaged in phonotaxis, she's reorienting, but if this mechanism were not in place, the optomotor reflex would cause the cricket to immediately reorient back where she was facing before she had turned in the direction of the sound. This efference copy inhibits the optomotor reflex by kind of predicting where the cricket should face given the phonotaxis that she is engaged in. So she can kind of phonotaxate and not automatically turn out because this efference copy is saying basically, no, this is the right visual information, this is what we should be doing, we don't need to reorient ourselves. And again, it's doing this in a direct sense act kind of way, and even this inhibition of the optomotor reflex by the efference copy during phonotaxis is a bit like the subsumption architecture of a robot such as Herbert. So, very interesting. So cricket phonotaxis is a great way to illustrate interest in these complete but low-level systems within the field of artificial life. And that's what Barbara Webb was all about by implementing this stuff in a robot cricket. A robot cricket that counts as a behavior-based robot and not perhaps a classical robot like Shaky, which operates with complex representations and central planning. Rather, not to sound like a broken record, the robot cricket and the biological cricket are actually much more like one of Rodney Brooks's behavior-based robots, and not a robot like Shaky. All right, speaking of robots, let's move on to talk about some walking robots. And we're going to start off with our famous example of Honda's Asimo, which is a great robot, really cool, very cute, but actually not very efficient and not a very good model of how real creatures walk. So let's take a look at Asimo now. So if you see a video of Asimo walking around and doing things, it's actually pretty impressive. On slide 12, I have a link to a video of the latest iteration of Asimo in action. You can also find that link in the description to this video. But go ahead and watch it before you continue with this lecture. Now, Asimo can climb stairs and walk around and do things which seem quite impressive. But actually, Asimo is quite energy inefficient. It has to control all of these powered joints and servos and maintain balance. And it actually has a high specific cost of transport compared to a human being. Specific cost of transport is a measure of the energy it takes to move a specific unit of weight, a specific unit of distance. So it's energy used divided by weight times distance traveled, for those who are maybe a little bit interested in the engineering side of things. Now, Asimo has a specific cost of transport of 3.2. Most humans, or I would just say humans, I suppose, have an average specific cost of transport of 0.2, which is much more efficient than a robot like Asimo. Indeed, when Asimo walks, it doesn't just use precise but energy-intensive systems to walk. It also has to represent the environment in a detailed way. It has to form a plan, execute the plan. So Asimo is very much like Shaky in that respect. It's a very traditional robot, but it's not very efficient. We could be more efficient if we took some inspiration from the way that biological creatures walk. Now, when real biological creatures walk, like human beings or dogs or cats or whatever kind of creature, they exploit mass properties and biomechanical couplings in their musculoskeletal systems. They take advantage of properties of their morphology in order to make walking more efficient. So the way that human beings exploit their bodies and the way that our bodies are designed, for example, remember, designed, uses our mass, the terrain, such that our walking action depends really on not so much, thinking about every step we take, but exploiting the properties of our body and the terrain, the body and world interface, if you like. And we can see this in dynamic walkers, for example. Passive dynamic walkers and just powered dynamic walkers as well. They use passive dynamics to achieve very complicated walking actions. Children's toys in the 19th century would be made like this, a little humanoid figure that would walk down a ramp or be pulled by a string and would walk. But without a power source, it would just exploit its mass properties, its bodily form, perhaps a slope with some gravity pulling on it, and it would walk. No engine, no power source, no CPU. And I think, like these walkers, we too exploit these passive dynamics. We kind of walk not so much in a step-by-step way where we have to think about every step we take, but we're walking in a way where we're like continually falling forward all the time, if that makes any sense to you. Perhaps I can illustrate this with a really cool example. Some of you may have heard of Theo Janssen's strand beasts. What are strand beasts? Check the video in the description or the link on slide number 12. These strand beasts are dynamic walkers. They often include a power source like wind, perhaps also water, or perhaps just gravity like a passive dynamic walker. But Janssen builds these intricate machines that walk around on the beach. I think that's what strand beast translates to, is a beach animal, actually. But in any case, these strand beasts are like dynamic walkers, and they walk around, and it's very fascinating to watch them move. But the best example for our purposes would be one of Collins's passive dynamic robots. And again, link in the description, link to a video on slide number 13. And the strand beast link is also on slide 13. I thought I said it was on slide 12. In any case, check out the video of Collins' passive dynamic robot, which has no power source at all. It can be led around by a tether or by a mechanical tether, a human pulling a tether or a mechanical tether. It can walk down a slope, being powered by gravity, and it exploits body design, mass properties, such that it kind of walks in a controlled falling forward. So that is what a dynamic walker does. And it does this without a power source, without central planning, with a CPU and complex representations. It's just basically a skeleton. that because of its mass properties, its musculoskeletal properties, and the properties of its environment, will just walk passively. Very fascinating stuff. But okay, we don't want our robots to be completely passive and need a human walking them around, or be equipped with a sail to walk down the beach. We want to have some powered locomotion in our robots. But if a passive dynamic body is equipped with a power source and it has really good passive dynamics, then we can achieve powered walking in a very energy efficient way. We can be much more energy efficient than Asimo is. For example, we could build robots with advanced control systems that can learn to take advantage of passive dynamics, and that way they could achieve very energy efficient transport. Robo-Toddler was one such robot that could do this. It could learn to change speeds, go back and forward, turn, and even adapt to different kinds of terrain, smooth versus rough, and so forth. But it's much more energy efficient than Asimo. Remember, Asimo had a specific cost of transport of 3.2, but robots like Robo-Toddler and other robots like the one designed by Collins, the passive dynamic robot designed by Collins, achieve a specific cost of transport of 0.2, which is on a par with the specific cost of transport of a human being. And we need to pursue this approach because there are limits to how efficient we can be with further advances in the kinds of control types that Asimo possesses, for example. Asimo, as Clark writes in this chapter, is like a helicopter. And passive dynamic robots might be like gliders. Powered passive dynamic robots would be like airplanes. No matter how well designed, Asimo is just never going to be as energy efficient as a powered passive dynamic robot. Just as no matter how well designed your helicopter is, it's just not going to be as energy efficient as an airplane or a glider. Because an airplane and a glider exploits passive dynamics in its environment in a way that a helicopter can't, right? So Asimo's like the helicopter, dynamics robots like airplanes and gliders. That should make that a little more concrete for you. These powered passive robots conform to something that Pfeiffer and Bonnegard call the principle of ecological design. What is that? Well, it basically involves a match between the complexities of the agent's sensory, motor, and neural systems in a given task domain. We need to balance this task distribution between the morphology of the agent, what the agent is made out of, how it is controlled, and what the environment is like. So, excuse me. So, the coevolution of morphology with control can spread problem solving between the brain, body, and a world in the same way that we saw with robots like Herbert in the previous example. And the COG and the BabyBot platforms have actually been used this way. And they do things in a way that, by the way, is very similar to the way that human infants do things. They manipulate objects, and that's how they learn about object boundaries. They learn about these boundaries of objects and the environment by poking things and shoving them and moving them around. It's the same thing that a human infant does. Put something in a human infant's hands or dangle it in front of it, and it will try and reach out and move it around and shake it and bang it against something else. The human infant is trying to spread problem solving and learning about the world out into the world through its infant body. And by doing it this way, by poking at the world, that is how it learns about the world and how to behave in the world. We can make robots that adopt a similar strategy if we follow the principle of ecological design. So, a major strand in contemporary robotics is therefore to stress the importance of distributing problem solving across the brain, the body, and the world. And this is very different from the traditional sense, the traditional picture in robots and AI. Okay, so walking robots have nicely illustrated our second theme, the importance of the mind, the body, and the environment. Let's move on to the third theme, which is the emphasis that's placed on emergence and collective effects. We're going to start out with a little discussion of Boyd flocking. I'll explain what Boyds are in a moment. And then we will turn to termite nest building. All right, let's get started with that. All right, so the importance of emergence and collective effects. I did say earlier that although there's some agreement insofar as emergence is usually thought of as complexity arising from simplicity, there is some disagreement about what that means and how best to understand that. But we're going to get to that in part 2 of this lecture. For now, as an example of emergence, consider the flocking behavior of birds or the schooling behavior of fish. You know how all the birds and fish seem to move as one fluid organism. It's very interesting to see, almost hypnotic and very, very cool. How do they do that? Well, one possibility was uncovered by Reynolds in the 1980s, who was actually developing this, all of this stuff I'm about to tell you about, as a tool for computer animation. But he implemented flocking behavior using simulated birds called Boyds. Now, these Boyds, there will be a flock of them, and they're governed by only 3 simple rules, at least the ones I'm going to show you in the video were. The rules were for each individual Boyd to stay near a mass of other Boyds, to match the velocity of its neighbors, and not to get too close to any other individual Boyd. With only these 3 rules, the Boyd flocks, well, demonstrated flocking behavior. They can even avoid obstacles and find food and so on. And you can take a look at a video of the Boyd simulation by following the link on slide 16, or by clicking the link down in the discussion, in the description section of the video. Now, Reynolds claims that while the Boyds are merely simulated birds, the flocking behavior is in fact real. And this complicated flocking behavior, or schooling behavior if you want to talk about fish, is an example of emergence. Complicated dances of thousands of birds in the sky as a seemingly whole entity are actually explained by each agent in that flock following a number of very simple rules. So Boyds are a really great showcase of complexity emerging from agent-agent interaction. But keeping with the theme of this chapter and the previous chapter, what is really interesting to a cognitive scientist is not just agent-agent interaction, but agent-environment interaction. So here, of course, is where we come to termite nest building. So how do termites build their nests? We need to brush up on our termite construction here. So the principle governing the behavior that allows termites to construct nests is called a stigmergic routine. What is a stigmergic routine? Well, let's look at stigmergy first. Stigmergy comes from the word stigma, which is the ancient Greek for sign, and ergon, the ancient Greek word for work. So stigmergy is like sign work, if you like. And a stigmergic routine is a repeated agent-environment interaction that sort of creates this collective process, like the construction of a termite nest. All these individual termites are following a simple set of rules that allow these agents to interact with one another and with the environment in such a way that complexity arises out of these simple rules or stigmergic routines. So how does it work specifically for termites, you ask? Well, termites like to roll up little balls of mud. And they like to insert little chemical traces into their balls of mud, little pheromone traces. And they like to pick up the balls and deposit them where the trace is strongest. So you have termites rolling up balls of mud and inserting chemical traces into their mud balls, and they're just kind of leaving them there at first. It's all kind of random mud ball placement. But after a while, mud balls start to pile up because the initial mud balls act as an attractive force to the termites. And the termites want to deposit their mud balls where the trace is strongest. So if there's one random mud ball there, another termite will deposit a mud ball beside it. So now there's two mud balls and the trace is strongest. More termites deposit more mud balls. And before we know it, the mud balls start to pile up and columns are beginning to form. The termites have no plan for their nest. There's no nest blueprint in their termite brains that they're following. They're just depositing their pheromone-laden mud balls where there are the most pheromone-laden mud balls. And over time, they begin to build these big columns. What happens next? Well, some of the columns just happen to be close to one another. So the scent from one of these columns causes the termites to deposit mud balls on another column that's, on the side that's closest to the neighboring column. So we have two columns like this, perhaps, and because they're close to one another, the termites want to deposit more mud balls on this end of this column and on this end of this column, because those are the ends that face one another. So they continue doing this on the sides of the columns that are closest to one another, and the columns get larger and heavier, and they begin to incline together due to their weight, and they create a sort of archway, and the stigmergic routine continues, and eventually the termites start to build cells, chambers, tunnels, and before we know it, we've got a whole termite nest. And we've actually implemented similar stigmergic routines in computer simulations and with small robots. So we've recreated this kind of stigmergic behavior in artificial cognitive systems, in virtual environments, and with robotic agents in a real physical environment. And similar routines to this, by the way, are what allow other kinds of insects like wasps and bees to do what they do. It allows wasps and bees to build hives and honeycombs. It allows ants to build nests and help to organize their insect societies, right? Now, in all cases of this, of insect stigmergy, the collective activity of nest building or hive building or whatever is not coordinated by regular communication or signaling. And I know what you're thinking here. You're thinking, what about the queen termite or the queen bee or the queen ant that communicates with pheromones? Yes, the queen can direct an ant to, say, start building something or start moving these larvae over here or whatever. The queen can provide some direction, but the behavior itself is not directed. It's a stigmergic routine, okay? So all of this is done without any kind of coordinated communication or signaling. The termites or the ants or the bees or wasps or whomever don't plan their nest and then follow the plan. Rather, signals are channeled through the termites' work, ergon, stigmergy, work, and through the environmental structures. So this is a great example of emergence, of complexity emerging from simplicity. Now, I don't want to say too much more about emergence now, because we are going to spend a good amount of time talking about it next time. But I just wanted to provide you with an illustrative example of emergence via the stigmergic routines of termites and other insects. So I think what I'll try and do is wrap it up now for the day. Let's try and summarize things. We've seen today that work on robotics and on artificial life tries to reimagine the study of the mind, and it does so by emphasizing a few different things, as we've seen. It emphasizes the unexpected ways in which multiple factors like morphology of the body, the nature of the mind, and the environment all converge together in natural problem solving. Whether we're talking about the flight of birds, termite nest building, cricket phonotaxis, what have you. We've seen that some of these systems have the ability to support robust adaptive responses, again, with nest building or phonotaxis or flocking, without any kind of central control or planning. So again, this is very different from the classical symbolic picture of AI that we started learning about at the beginning of this class. And we've also seen that the potency of simple rules, or rather that simple rules have this power along with behavioral routines, simple behavioral routines. Each of these has, the ability to operate against a rich backdrop of environmental structures and other agents. We saw this especially in our discussion of complexity and of emergence, complexity arising from simplicity. Are there concerns with everything we've talked about today? Yes, absolutely there are, but that is what we will look at next time. So, just to recap the three themes we've covered today, we covered interest in complete but low-level systems. So these are whole, relatively autonomous systems that sense and act in real environments. This is what Dennett argued we should be doing in his 1978 paper, Why Not the Whole Iguana? And we illustrated this with a look at Barbara Webb's work on cricket phonotaxis. We then turned to the second theme, the recognition in robotics and artificial life research of the complex contributions of the body, action, and the environmental context to adaptive behavior and natural problem solving. We saw this with walking robots, of course. And finally, we saw how research in robotics and artificial life pays special attention to emergence and collective effects. And of course, that's what we looked at with our Boyd flocking and our termite nest building examples. Next time, we're going to turn to the discussion section of Chapter 6. And more importantly, for our next lecture, I will share some important information about the upcoming midterm. The midterm, as you know, is set to take place over Reading Week, but I may push it back a few days. I may extend it a little bit. I have yet to decide exactly what I'm going to do in that regard, but I will let you know at the end of the next lecture. And what I will also do is let you know a little bit more about the structure of the midterm. What kind of questions will you have to complete? How will you complete them? What time limits will you have? So on and so forth. So I will cover all of that at the end of next lecture after we've discussed the points of discussion in Chapter 6 of Clark's book, Mindware. All right, that is all for today. Again, my apologies for being late with this one. I am having a heck of a time keeping caught up. I imagine all of you are probably in a similar boat, so I hope that this is not causing any issue for you. But by the end of Reading Week, we should be back on schedule. And in any case, if you need some flexibility with assignments, critical responses, if you've got a heavy workload in another class, and you need me to work with you regarding due dates and whatnot, let me know. Please, let me know. And let me know how you're doing. In the meantime, I hope you're all doing well. I hope you're taking care of yourselves and one another and those close to you, your friends and family. And I will see you next time for our next lecture where we wrap up Chapter 6. All right. Bye for now, everyone.